So I was thinking, since we had already made our Jacobi iterations, we might as well try to apply it somewhere else. Somewhere else where we have some derivatives and might want to, or a type of derivatives, and might want to find the values that they're derived from. So what we're going to do is we're going to turn a normal map into a height map. So you'll remember that we previously did the opposite. We previously made a normal map out of a height map. And the way we did this was we took the gradient in much the same way as we did with the Sobel. And then we did some mathy trigonometry on it. And with that, we basically got the normals that we needed. So now we need to go the other way, because remember when we used the Jacobi iterations for the fluids, we were working with gradients. We were working with vectors in 2 dimensions of varying intensity. And it's very much the same as when we took the gradient in the with the Sobel operator. So we basically want to take a normal map, turn it into a gradient map again, take that, find the divergence, and then use that divergence to calculate a new quote unquote pressure field. And then that will be our height map. And it'll look a little bit like this. And you can see that because we are using not the most perfect solver in the world, there's still a little bit of curvature, but it's getting a lot of the geometry right. If I sort of like just intersect with it, you can see that it really gets the angle of the polygons of this torus here. And yeah, it's not too bad. So let's just have a look at what we need to have a look at. And the way that this one is set up is basically just that we first on begin play, we calculate the divergence, and then after we've calculated divergence, we just every frame keep doing another number of Jacobi iterations. I think we are doing somewhat upwards of just 10 per frame. So you can see it accounts for quite a lot when you sum up over all the frames that we are waiting until we're seeing a good result, but that is the shortcoming of Jacobi iterations. There are better methods than Jacobi iterations. There is successive over relaxation. There is also multigrid. There's also the option of using fast Fourier transform to convert into a spectral space and then solving it's called partial differential equations, solving it as ordinary differential equations and converting back again. There are probably even better methods, but that's the one I know that is most likely to give a precise result relatively fast. But as you can probably hear from it, it's a whole lot more involved than, just blur and compensate and blur and compensate. We still get some pretty good results. So let's look at a normal map and figure out how to convert it into a gradient map. We can say that the places where we have this light purplish blue is the neutral ones. This is where we want no gradient. And then wherever it takes on a reddish or greenish color, or deep purple color, we have some sort of gradient going on. So the reason why this is a light blue is actually because we can't have negative values in our textures. In reality, this should be strong blue because it just denotes a value of 1 in the Z direction and then 0 in the red and green direction. But because red and green needs to be able to go negative, well, we need to keep neutral as a mid value, so 0.5 or 127 in integer values. So now let's try comparing a normal to the unit circle with the trigonometric functions. So let's say it's neutral, which would usually just mean a value of 0 in x, 0 in y, and 1 in z. That would be the equivalent of no degrees rotation. And at this point, we can see we have cosine of 1 and we have a sine here of 0. And as we start increasing the angle, then of course we see that the cosine gets smaller and the sine gets larger. And what we know is that as we increase this angle, we want a value that also increases. It will start at 0 and it will grow to basically infinity. So if you look here, there is a value on here that does that. And which one is that? Well, it's the blue. It's the tangent. If you know some trigonometry, you know that you can find the tangent by dividing the sine with the cosine. And so when we are here at no angle at all, we can say, well, the cosine must be the z value because that is what is 1 when there is no rotation. And sine must be some sort of combination of the red and the green channel, the xy components. And so if we take xy and divide it by z, so we take red, green and divide it by blue, then we get a value that can start at when there is no information or no change of angle at 0, and then the bigger that change is, the more it grows towards infinity. So that is basically what we do inside this normal to derivative material. We first take a normal map, which we read in as a linear color. We then convert it from the 0, 1 to the -1 to 1, which means that we actually multiply it by 2 and subtract 1 so that we get black wherever we're having a, let's call it a neutral normal. Then after that, we then do the division where we have taken just the red, green divided by blue, and then we make sure that we do not go above 5,000 because already at 5,000 it starts to be fairly large values to run the solver on. And if we went closer to infinity, we would start getting these rounding errors and everything would explode. We then multiply by -1, which might seem a bit strange to do, but remember that we did the same thing when we went the other way and we have to flip back again. And that's basically it. That's how we get our derivatives from our normals. The rest of it is basically just repeating what we did inside the fluid solver. We started out while calculating divergence, first doing the derivative and then taking the derivative and using it to calculate the divergence. And then every frame we are just taking that divergence texture and then we're doing another iteration on our pressure texture. I guess we shouldn't call it the pressure texture in this case, but it's pretty much the same thing. The thing to note is that we are actually basically just, if you're looking over here, at least for the divergence and the iteration material, we're just reusing the ones that we got from the fluids. So that is your crash course in partial differential equation solvers and how to calculate a field from its derivatives. And we have now used it both to get fluid simulation and to generate a height map from a normal map.